Okay, so what we're going to do now is we're going to talk about how, trig functions mainly rely on right triangles. In fact, they're defined to work with right triangles. So as you can recall, the first time you probably heard of trig functions is you learn of the basic opposite over hypotenuse for sine, for example. And notice how when we say hypotenuse, well, the only triangles that have hypotenuse are right triangles. So we can basically say that, look, we know that trig functions rely on right triangles. That is, if we have the following right triangle, and let's call this angle alpha, let's call this angle beta, and this is a right angle. Let's call this side B, this side A, and this side C. So we know by definition, if we think back to the first time we saw our trig functions, for instance, sine of alpha, we learned was opposite over hypotenuse, where in our picture from alpha's perspective, opposite would be A over hypotenuse, which would be C. And then we have cosine of alpha is adjacent over hypotenuse. And that from alpha's perspective, adjacent is B, hypotenuse is C. And we have tangent of alpha, which is opposite over adjacent, which is going to be, in this case, opposite over adjacent, which is A over B. Okay, and then obviously we can say, hey, depending on what angle's perspective we're looking at, for example, if I have sine of beta, well, from this angle's perspective, opposite over hypotenuse is what? B over C. So that'll be B over C. And then we have cosine of beta, which is adjacent over hypotenuse, and that's A over C. And then tangent of beta would be, from this angle's perspective, opposite over adjacent, which is B over A. Okay, so these definitions of these trig functions, if you remember, we talked about it last chapter also, which was we wrote sine, cosine, and tangent in terms of x, y, and r, which is our main interest anyway. But what's going to happen now is we're going to kind of take a different approach of this, where we'll be given the angle measure, which, if you remember, last chapter, other than the quadrantals, we weren't given the angle measure, but we'll be given the angle measure and we'll be asked to find the exact value of trig functions. Now, I'll give you kind of like a step-by-step explanation as to what we're going to be doing or how we'll do this, and then we will do some examples and we'll follow these steps. So the key here is we want to find our exact values of trig functions. So with that said, let's kind of talk about how we're going to be doing this. And for me personally, I'm a very, very visual learner, especially in trig. We could almost visualize anything we work with. So I'll kind of show you my thought process and how I work through this, because I find it most convenient to work with it this way. So we're going to say, when given an angle, so we'll be given an angle, so they'll say, hey, for example, 30 degrees. They'll give you the angle, and we'll be asked to find the exact values of the trig functions. Now, which trig function they ask us, it doesn't matter because we have the definition, right? So of the trig functions, these are the steps we'll follow. So we will follow these steps. Okay, so the first step for me is I'm going to draw the angle out. And if you remember last chapter, we said it's very important that we draw angles in standard position. So the first thing I'm going to do is I'm going to say draw the angle in standard position. Okay, and then once we do that, then the second step will be we're going to create a right triangle. Okay, now how are we going to create this right triangle? Now let's be careful because we have to be very specific in how we create the right triangle. So we're going to create a right triangle by choosing any point on the terminal side. So the good news also is we're going to choose any point on the terminal side, which is kind of nice. So regardless of what point we choose, it really makes no difference, because if you remember, something nice happens when we work with these. We're going to get similar triangles, so our ratios are going to be the same. So when we're saying any point, we really mean any point, as long as it's on the terminal side of the angle, and you have to draw it straight to the x-axis. Okay, so that's what you'll do. And then what's going to happen, and this is the nice thing that you're going to notice, if I don't allow you to use a calculator, which the trig functions that you're going to work with without calculators, they should give you the nice triangles to work with. So what we're going to do is we're then in step 3, we're going to say, look, pick any side, and I'll underline any. And it really doesn't matter which side you pick. I mean, there's obviously ways around it. You could just, through strategy, you could say, hey, I'm better off picking this side, but it really makes no difference. Pick any side of the triangle and assign it any appropriate value you would like. Now when I say appropriate, the reason why I'm saying any appropriate value, see, you can pick that side and call it any value you want, but you have to be careful, because if my angle, let's say, is in quadrant 2, for instance, my x value should represent a negative number and the y value should represent a positive number. So it's going to look like we're saying that the length of the sides are negative. That's not the case. We're just going to use negative numbers for the sides of the triangle, just to say, hey, for example, if I'm moving to the left, that's in a negative direction, so we're going to call it a negative number. Other than that, when I say appropriate value, it's because we need to make sure that we choose the correct positive and negative numbers, okay? So that's one thing that I mean. But as far as the number, the value itself goes, other than the sign, you can choose it to be anything. And hopefully that'll become even clearer once we do an example and you'll see the steps that we go through. So then step 4, once you do that, once you create your triangle, you're going to notice that you're going to have those nice triangles. So it's either going to be a 30, 60, 90 or a 45, 45, 90. So we're going to say use the ideas of 30, 60, 90 or 45, 45, 90 triangles to find the other 2 missing sides. Which, when you do that, that will then, when we find the missing sides, this word is sides, which gives us x, y, and r. So which gives us x, y, and r. And once we have x, y, and r, then we can give the exact values of the trig function. So then comes the easy part. Then you can give the exact values of the trig functions. And one comment I want to make. The only time where we're not using the calculator, where you won't get a 30, 60, 90 or 45, 45, 90 triangle, is if you have quadrantals. And if you remember, we did that in chapter 1, where we found the exact values when we use 90 degrees or 270 degrees and so on. Okay, so let's look at our first example. We're going to say find sine of theta, cosine of theta, and tangent of theta given A, theta is 30 degrees, B, theta is 45 degrees, and C, theta is 60 degrees. So let's do the first one together, and then I would recommend that you pause the video and do the other two together by yourself, and then you can check to see if you did the steps right. So notice how they're giving us the angle. And remember, since we have the angle, we're going to replace theta with 30 degrees for this one. But before we do that, before we find sine theta, cosine theta, or sine of 30, cosine of 30, and tangent of 30, we need to follow the steps that I gave you earlier. So the first thing I'm going to do is what? Draw my 30-degree angle in standard position. So this is 30 degrees. And then what did I say? The second step was what? Choose any point on the terminal side and go straight down to the x-axis and make a right triangle. Okay? So now notice what I just created. That's 90, that's 30, then this upper angle has to be 60 degrees. So I've created a 30, 60, 90 triangle. So then what did I say? Pick any side, and if you remember for the 30, 60, 90 triangles, we prefer to get the shortest side first. So if it's up to me to pick any side, I'm going to pick the side opposite the 30 degrees because that's the shortest. And since I'm moving upwards, my y value is going to be positive. So if it's up to me to pick any number, the nicest number to work with is 1. So I'm going to call this side 1. Okay, now the other two sides I cannot make up and do what I want, choose something else for them. Now what I need to do, if you remember in last chapter we said, hey, if I have a 30, 60, 90 triangle and I have one of the sides, so I've picked one, and by the way, it really doesn't matter if you're wondering, hey, did you really have to choose one? I didn't. So if you want, you can call this 2, or you can call it 10 or 1,000, and you'll see that you'll get the same answer as I do. But usually if it's up to me, I stick to picking 1 because it's the most convenient number. So here's what we know. From a 30, 60, 90 triangle, if I have the shorter leg, I could find the hypotenuse because all I need to do is grab the shorter leg and double it. So 1 times 2 is 2. And then if I have the shorter leg, I could find the longer leg just by grabbing the shorter leg and multiplying it by rad 3. So 1 times rad 3 is just rad 3. Now notice what I just found. This is x, this is y, this is r. So I could now answer the questions. So sine of 30 degrees, now notice how I'm writing the angle because I know what the angle is what? Y over r, which is 1/2. Cosine of 30 degrees is what? X over r, which is rad 3 over 2. And then tangent of 30 degrees is y over x, which is 1 over rad 3. And if we want to rationalize this, just multiply top and bottom by rad 3, and you get rad 3 over 3. Okay, and there you have it. So I would recommend that you pause the video, do these two on your own, and then play it again and see how your answers match up with mine. But with that said, let's kind of continue with this. So if I'm solving the sine, cosine, and tangent of 45 degrees, same steps, right? So the first thing we want to do is we want to draw the 45-degree angle. And then I'm going to pick a point, draw my right triangle, and then I get what? A 45, 45, 90 triangle here. So then I pick a side, and see, the nice thing is here if I know one of the legs, so if I pick this leg, let's say, and I call it 1, then from a 45, 45, 90 triangle, what do I know? The other leg is also 1, then the hypotenuse is rad 2. So now I could answer, I have my x, y, and r. So sine of 45 degrees is y over r, which is 1 over rad 2. And if I rationalize that, I get rad 2 over 2. And then we have cosine of 45 degrees, which is x over r, so that's 1 over rad 2. And if I rationalize that, that's rad 2 over 2. And then tangent of 45 degrees is what? Y over x, which is 1 over 1. And that's 1. Okay? So now we do the same for 60 degrees. So hopefully you're starting to see how straightforward and convenient this is, because all I'm really working with are 30, 60, 90, and 45, 45, 90 triangles. And once you have the picture, everything else falls into place. It just comes out so nice. So if this is 60 degrees, once again, pick any point on a terminal side, make your right triangle. So then this becomes 30. So now I have a 30, 60, 90 triangle. So once again, to pick a side, I generally like the side that's opposite the shortest leg, or the shortest leg, which I'm going to pick this and call this 1. So then what would the longer leg be? It would just be 1 times rad 3, which is rad 3. And then the hypotenuse would be 1 times 2, which is 2. So now I could say, look, sine of 60 degrees is y over r, so that's rad 3 over 2. Cosine of 60 degrees is x over r, which is 1 over 2. And tangent of 60 degrees is y over x, which is rad 3 over 1, and that's rad 3. Okay, so that's basically how you would work with this whenever you're given an angle. Now, we mainly worked with angles in quadrant 1. Later on, we will go into different quadrants, and you'll see how there's going to be one minor tweak or one minor difference, which we'll talk about that when we get to it. But let's continue on and do example 2. So for this one, notice how now they're saying, look, given sine of theta is 3/5. Now, let me point something out here. See, for this one, notice how they haven't given us the angle, but they've given us the ratio, which we can figure out what the x, y, and r are. So kind of example 2 is kind of different. If you compare example 2 to example 1, what happened in example 1, we were given the angle and we were asked to find the exact value. For this one, we really aren't given the angle, right, because they're calling the angle theta, but we've been given the exact value, which will give us enough information to find whatever the question is going to be. So, and theta is an acute angle. Find the remaining trig functions. Okay, so for this one, notice how when they say theta is an acute angle, what does that mean? It's between 0 and 90 degrees. So I'm just going to draw just a generic picture. So there's theta. Now, why is that important? You'll see why that's important in a minute. So, given that sine of theta is 3 over 5, if you remember, by definition, sine is what? It's y over r. And what is it that we know? This is y, this is r, and we know that, look, since I'm in quadrant 1, or theta is acute, y has to be positive, so does x, right? So that's why they're telling us this information. This information is important for us to figure out, hey, what's y, what's r, what's x? And you'll see why in a minute. So we know that y is 3, r is 5. Now, to be able to find the remaining trig functions, I also need to find x. Now, how could I find x? Well, I could use the idea of our Pythagorean, or the Pythagorean theorem, can't I? Because if I come back to this picture, I know that r is 5, y is 3, I just don't know what x is. But we know that we can say x squared plus 3 squared is equal to 5 squared, which gives me what? X squared plus 9 equals to 25. If I subtract 9 from both sides, I get x squared equals to 16. And when I solve for x and I take the square root, I get x equals to plus or minus 4. Now see, here's the problem. Do I take the positive 4 or the negative 4? And that's where this information, where theta is an acute angle, that's where this information comes in handy. Which, if it's acute, what does that mean? I'm moving to the right, so x has to be positive 4. So x is going to be positive 4. We don't take the negative. So once we have this, now comes the easy part. Well, what would cosine of theta be? That's x over r, which is 4 over 5. What's tangent of theta? That's y over x, which is 3 over 4. And then we have the reciprocals, don't we? We have cosecant of theta, which is the reciprocal of sine, which would be r over y. So that's 5 over 3. We have secant of theta, which is the reciprocal of cosine, which would be r over x, which would be 5 over 4. And lastly, we have cotangent of theta, which is the reciprocal of tangent, which is x over y, which would be 4 over 3. Okay, so once again, if you notice how example 1 and 2, the similarities were, we just had to find the x, y's, and r's. Okay, so moving on to one more example, and then we'll talk about our last idea, and we'll do a couple more examples, and that will do it. So given the triangle, and I'm drawing this out, 20, 21, and 29. This is angle B. That's a right angle. So we have a right triangle, which is good. We want to identify the coordinates of the point on the terminal side of angle B in standard position. Okay, so all they're saying in this question is, hey, grab this triangle and redraw angle B where angle B is in standard position. And then once you do that, then identify the points of the terminal side of angle B. Give me the coordinates of the point. So let's not worry about the coordinates just yet. Let's first draw angle B in standard position. Now remember, if it's in standard position, we need to make sure that its initial side is on the positive x-axis. So I can call basically the initial side this, for instance, which would be, let's say, that would be 29. And then what am I going to do? I'm going to rotate. Well, actually, let's be careful here, because the 29, actually, that's the hypotenuse. So if I were to draw it out like the earlier examples, never mind. This has to be the side there, because I have to create a right triangle that looks like that, because if you remember, my right triangles were created like that. So this is going to be angle B. Notice how I've put it in standard position. So this shouldn't be the 29, actually. This should be that 20, right? So this is 20. The 29 has to be there, because if you remember, when we draw our right triangles, the right angle always has to go to the x-axis. So if this is 20, that's 29, then this, which would end up there, is 21. So once we have that, now we want the coordinates of that point. But that comes the easy part, because if I start from the origin, how do I get to that point? I need to move to the right 20 units, and then I need to move up 21 units. So the coordinate would be x comma y. So this is my x, right? This is how much I move to the right. That's 20. And then the y is how much I move up, right? So that's the x, that's the y. So the y value would be 21. Okay? So once you identify the picture appropriately, then you could easily figure out exactly what it looks like. Okay, so the last concept, or the last idea we're going to talk about, which we'll see will play an important role as we go along in this class, has to do with cofunctions. So what we'll notice is there will be certain values where two different trig functions will give you the same exact value. And that's not a coincidence. That's because of cofunctions. So let's first define what cofunctions are. So we would say that two trig functions are said to be cofunctions if they have the same exact value. So in other words, you take their ratio, you get the same thing, or when their angles are complementary. Okay, so if you remember, we talked about what it means for angles to be complementary. They add up to 90 degrees. So there's two conditions that need to be set. The first one is their exact values have to be the same and their angles have to be complementary. So what we're saying is their angles clearly don't have to be the same, but as long as they add up to 90 degrees. Okay, there's actually, so we could actually show how, or we could actually show visually. So this is kind of like a visual representation. So as I've mentioned, I actually like to show things visually. To me, if I could draw something and make sense of it visually, it totally, the problem totally makes sense then. So the thing I'm going to do is, the way we're going to discover our cofunctions is this. I'm going to just draw a right triangle. And why am I drawing a right triangle? Because trig functions rely on right triangles. If I don't have a right triangle, I can't use trig functions, okay? So if that's angle A, this would be side A. If that's angle B, this would be side B. If that's angle C, this would be side C. So let's start off with kind of saying, starting off with an angle. So let's say I pick angle A, and I ask you guys, hey, what's the sine of angle A? Okay, so there's no specific reason why I picked angle A, and there's no specific reason why I picked the trig function sine. I just said, hey, let's do this. So if you were to do this, and if I asked you, hey guys, could you tell me what the sine of angle A is? You'd say, well, from angle A's perspective, what do I get? It's opposite, which is A, over hypotenuse, which is C. So it'll be A over C. So my question to you now is, can you find another angle where if I were to use a different trig function, where I would still get A over C, or I would get the same value as this? And the answer should be, yes, you can. And it would be which angle? You would pick angle B, because how do I get A over C from angle B? It's adjacent over hypotenuse. And which trig function is adjacent over hypotenuse? It's cosine of B. Now look at what happens here. Sine of A and cosine of B both give you the same ratio. It's A over C. So they have the same exact value. And what is it that we notice about angle A and B? What would I get if I added A and B together? Well, if you remember last chapter, we said all the angles of a triangle add up to 180. So if this is 90, then A plus B has to add up to 90 as well, because if I want the whole thing to be 180, these two should be 90, that should be 90, which gives me the 180. So we could say, look, notice A plus B is 90, which, what does that mean about A and B? That means they're complementary. So sure enough, what did we just discover here? This implies sine and cosine are cofunctions. Okay, so that's one pair of cofunctions. So, and that's a fact. So from now on, if I'd say, hey guys, tell me a pair of cofunctions, sine and cosine are cofunctions. How come? Because they satisfy this definition. Okay, so I'll also wonder, hey, how do I know these are cofunctions? Well, look at how these are defined. Okay, now the next one would be what? So let's now just take another trig function. Let's call cosecant of A, because this is easy, because cosecant is what? The reciprocal of sine. So then obviously cosecant of A would be sine of C over A, and then you'd say, hey, what would also give me C over A? It would just be the reciprocal of cosine, so it would be secant of B. So that one I think we got for free as well. So we could also say that cosecant and secant are cofunctions. And there's only a pair of trig functions left, which I think by now you know that the other two. So for example, if I had to take tangent of angle A, which what is the tangent of angle A? That would be opposite over adjacent, so that would be A over B. And if I were to ask you, hey, can you find me another trig function using angle B that would give me A over B? You say, well, what's adjacent over opposite? That's cotangent, which would be cotangent of B. So tangent and cotangent are cofunctions. Okay, so what is it that we're saying here? We're saying that, look, sine of A and cosine of B will always be equal to each other as long as what? Their angles are complementary. Cosecant and secant will always be equal to each other as long as their angles are complementary. So another way of putting this, so this is actually a property that you guys should know. It's the following: sine of theta will equal to cosine, And sine and cosine will not always equal to each other, except their angles have to add up to 90. So if the angle for sine is theta, then cosine has to be 90 minus theta. Now if you're wondering how I came up with the 90 minus theta, well, look at this. What's theta plus 90 minus theta? The thetas will cancel out and I get 90. So remember, I'm only telling you that sine and cosine are only equal only when their angles are 90 degrees, okay? Because we can't say that they're always equal. For instance, if we go back to the original example that I did for 30 degrees, for example, notice how sine of 30 is a half, cosine of 30 is rad 3 over 2. They're clearly not equal. But, however, look at 45 degrees. Sine of 45 is rad 2 over 2. Cosine of 45 is rad 2 over 2. Is it a coincidence that they're the same value? Of course not, because notice how 45 plus 45 is 90. So in that instance, they end up being equal. But I'm not by any means saying sine and cosine are always equal. The only time they'll be equal is if when their angles add up to 90 degrees. Okay? That's when sine and cosine end up being equal. So same thing with, obviously we could also say the same thing the other way. Cosine of theta is equal to sine of 90 minus theta. And then what are the other pairs of trig or cofunctions that we have? We know that cosecant of theta is equal to secant of 90 minus theta, or vice versa. You could say secant of theta is equal to cosecant of 90 minus theta. And then the last pair of cofunctions are tangent of theta is equal to cotangent of 90 minus theta, and cotangent of theta is equal to tangent of 90 minus theta. I'm basically trying to tell you the order doesn't matter where the 90 minus theta is, as long as the angles add up to 90 degrees. So you might want to box these. These are important to know. We'll use them as well. So in fact, let's look at our next example where we'll put these to use. So there's two more examples and then that will wrap up this section. So for example 4, we're going to say given sine of 62 degrees equals to 1 plus rad 7, find cosine of squared of 28 degrees. Okay, so now one thing I want to point out to you is when you see cosine squared 28 degrees, that means the same thing. It's just a cleaner way of writing this. That's the same thing as cosine of 28 degrees quantity squared. So in other words, if you know what cosine of 28 is, square it. So let's think of it this way. Notice how if we start off with the following. If sine of 62 degrees equals to 1 plus rad 7, now here's what I want to do. I somehow want to go from sine to cosine, don't I? Now the good news is we just talked about, hey, sine can be written as in terms of cosine, and they'll be equal as long as the angles add up to 90 degrees, because sine and cosine are cofunctions. So here's what we know. Sine of 62 degrees is the same thing as what? Cosine of what angle? Whatever this angle is. Remember, for them to be equal, it has to be complementary to 62. So this angle has to, I have to make sure I choose a number that adds up to 90, which should be 28, because 62 plus 28 is 90. Now look at how nice that is. Cosine of 28 is the same thing as sine of 62, and if we're asked to find cosine of 28 degrees squared, well, what is it that I know? So this implies cosine of 28 degrees equals to the same thing as sine of 62, which is 1 plus rad 7, which then would mean cosine of 28 degrees squared is the same thing as 1 plus rad 7 squared. Now remember, 1 plus rad 7, one common mistake people make, they say this is the same thing as 1 plus 7, which is 8, but you're forgetting to FOIL it. So when we have 1 plus rad 7 squared, I rewrite it as 1 plus rad 7 times 1 plus rad 7, which now I FOIL it out. I get 1 times 1, which is 1, plus 1 times rad 7 is rad 7, plus rad 7 times 1 is another rad 7, and then plus rad 7 times rad 7 is 7. So if I combine like terms, 1 plus 7 is 8, plus rad 7 plus rad 7, so this is 1 rad 7 plus 1 rad 7 is 2 rad 7. And there's our answer. Okay? So let's look at our last example. Given alpha and beta are complementary, verify cosine squared alpha is equal to 1 minus cosine squared beta. Okay, so now this is one of those verify problems. Remember where we're trying to prove this? So we started with the more complicated side, which is 1 minus cosine squared beta. Now, here's what I know here. I know that, wait a minute, so this one's a little tricky because I notice how for my beta has to switch to alpha. So, and what's the key here? We know that alpha and beta are complementary. And what's important about that is we know that when we add alpha and beta, they add up to 90, which means I could use the idea of cofunctions. So that I'm not concerned about yet. But here's what I do know. If you look at this, this is one of our Pythagorean identities. If you remember, we said sine squared alpha, or beta, plus cosine squared beta is equal to 1. So if I subtract cosine squared beta from both sides, what do I get? Sine squared beta is equal to 1 minus cosine squared beta. And I think this is the hardest transition to make. But what I could do is, if I switch 1 minus cosine squared beta to sine squared beta, which I can do, and remember, sine squared beta is the same thing as saying sine of beta squared. And what do I know? Since alpha and beta are complementary and sine and cosine are cofunctions, I could say sine of beta is the same thing as what? Cosine of alpha. And the square is there because of that. So remember, I'm just using the idea of cofunctions. Now, why was that important? Because look at what I want. I want cosine squared alpha, which that's the same thing as cosine alpha squared. So this and this are no different. They're the same thing. But if I want to rewrite it as cosine squared alpha, just to make it look clean, that will do it. So here's how we used the idea of cofunctions to verify 1 minus cosine squared beta is the same thing as cosine squared alpha. Okay, so this was one of those proofs that we talked about in chapter 1. We're just kind of revisiting it. So that wraps up our notes. As always, if you have questions, don't hesitate to email me, or you could ask me during office hours.